Administrative notes. I mean, obviously, the exam is on Thursday. At normal class time, I made it a little bit earlier and made the due date a little bit later, just so if you want to take your time, you have the ability to. It is 90 minutes, and if you start at like 7:20, it's not going to give you the full 90 minutes. It's only going to give you 10. So please start as early as possible. The 90 minutes again is just a bit of a buffer. It's only supposed to be 75, but I just want to make sure if you have to fill out something for some reason that you have a little more time. It'll be via web campus, and a question in chat was, what kind of questions should we expect for the exam? So it's a mixture of a bunch of different kinds of questions. So there is, I think, 18 questions. I know it says 20 on Canvas, but 2 of those are just you agreeing not to plagiarize, I guess. So there's 18 questions. I think about 2/5 of them are free response. About another 2/5 of it is multiple choice, but it's not necessarily like A, B, C, D, but more so here's a list of things, which of these apply generally. I think for the most part is what those kinds of questions were. And then 1 out of 5, about 1/5 of them are questions with code. And then it'll either ask you to write maybe 4 or 5 lines of code, something really, really short, or it'll be a block of code with either a class or a function or something like that, and you have to explain something about it or point out something that's wrong with the code or something like that. And then there's one question that's a program. And generally the programs are not that long, maybe 10 to 40 lines of code. And just as a reminder, these are all randomized. So there's a pool for each of these across all of the kinds of topics that we cover. So classes, inheritance, pointers, and that kind of stuff. And that's why this is about a fraction, is because it's a couple questions out of each of those categories and then one programming question. So it shouldn't really take that long. Probably not going to be the whole 90 minutes, but it's just there as a buffer. One other administrative note, well, somewhat administrative. I made a mistake last time. I was talking about the word finally for catching exceptions, and that's not a thing in C++. Inside C++, I was saying just catch the exception and put like the exception here, but if you want to catch everything, including things that are not exceptions like integers and floats and stuff, it's catch ... and then whatever block it is. So just a small correction on that. If you ever want to catch things that aren't exceptions, that's how you do it in C++ specifically. And then last note, just a reminder for office hours on, well, tomorrow, Wednesday, it's going to be a little bit later. It'll be 4 to 5 instead, just because I have a meeting to go to. Okay, so I think we're okay to do review then. Did anybody have any specific questions that you wanted to cover? And I'll pull up the list of topics as well. Okay, I don't see any questions yet, but if you have any, feel free to put them or just think about it a little bit and we'll come back to it. I guess we'll try to get through the rest of these first, and then if we have extra time, I think we'll just do some review questions as a class. We'll just come up with some. So I think we left off right after polymorphism on constructors. A constructor, if you remember, is just a special kind of function that you never really explicitly call. It's not like other functions where you give a name necessarily. Almost kind of is in C++, but it might get called in scenarios where you don't explicitly call it. And the way we define a constructor is we just give the name of the class and then some sort of parameter list. And like any other function, it can be overloaded, so we can have a bunch of different constructors. So we can have this one that takes some sort of parameters, and then maybe another one that just takes no parameters, and then we write whatever it does. And if you remember, this one's called the default constructor if it takes no parameters whatsoever. And a default constructor is implemented for you. If you implement no constructors whatsoever, it will automatically generate one for you, and it will do nothing. It just won't do anything. But if you explicitly write any constructor that is not the default constructor, then the compiler will no longer generate it for you, and that's why you may have seen some errors in the programs that you've been doing where it tells you that there's no default constructor. And it's because it needs one to be there in order for it to know about a default constructor. So question in chat, will we need to know about copy constructors? I don't think there's any questions on it on the exam, although it doesn't hurt to know about. If anything, you'll want to know about what goes into a copy constructor in C++ about pointers, specifically for the next assignment on operator overloading and then the next exam. But on this exam, I don't think there's any questions from what I remember. Right, so these are our constructors, and they get called whenever we instantiate an object. So in C++, there's several ways you can do that. We'll just write down here, I guess. So if you declare any sort of variable that's not a pointer and is an actual object, C++ will call the constructor, and specifically the default constructor. This one we'll call the default constructor. We can also explicitly ask for which constructor we want, either by using braces, or sorry, parentheses. So this will also call the default constructor, but it calls it explicitly, or whatever parameter list matches this one. Hello. So these are our three examples, and then we also have another one where we could do it like this, and specifically give the class name and then call it. And this allows us to set things past the variable line, whereas these three, the syntax requires you to do it directly on the line that you're declaring the variable. This one I could use in the declaration, or just if I was using the variable normally as well. Either way works. And it will go and call whatever constructor matches this specific argument call. And then remember, there was another way to do this, which was basically just the same thing, but instead we do it as the new keyword, and this will do the same thing as the above one. It'll call a constructor explicitly, and it will return it as a pointer to the object rather than just as the object itself. So these two are pretty similar, and really all of these pretty much do the same thing. So we can almost explicitly call our constructor, but it doesn't always necessarily happen that way, and there are occasionally some cases where if you copy something, it will call the constructor as well. But a constructor is called whenever you create an object, and that's the only time it's ever called. So you can never explicitly call a constructor ever again on the same object. Once it's called, it's done, and you can only call normal functions at that point. So after these creation, we can't do that. And because of that, we use constructors generally to initialize fields. For instance, if this class had an integer called n, then what I might do in this body is I might set n equal to some number, or I might have a constructor that takes some n that I want to initialize it to and sets it. And remember, if you use the same variable name as a member and as a local to your constructor function, then you'll need to use the this keyword in order to refer to this object and set this one here. So this one is this n, and this one is the other n. But generally we use a constructor to do anything that happens when you need to initialize a class object. And that's because it's only called when it's created, and so it's important to call it. Or it's important to do things that would need to be done at creation time only. Right, so let's do another example of this. Remember that, also another question in the chat, deconstructors are going to be on the exam too, I'm assuming. Yes, yeah, you're right. And we'll get to these deconstructors in a second, but yeah, you're right, that'll be on the exam. So remember, let's just say we had that one example from assignment 3, I think this was. We have a student class, and the student class has a constructor. Let's say it's public. Then this is going to, let's just say, have a string name that sets the name field that we would have presumably here. And remember, if we decide to inherit from a class like this, let's say we do undergrad, that inherits publicly from the student class. Then if I was to write a new constructor for this derived class that inherits from a class that already has a constructor, but I want to use that constructor, then remember the way you can do that is, let's just say this is string n for name, and then the undergrad has maybe some sort of status, I think was kind of what that was like. I think maybe it was the grad class, but I'm sure you get the idea. Then we're able to call a base class constructor using the colon. Student. And once you write this, you have access to any parameters that are to the left of it. So I have access to both the string n and the status s when I write this line of code that does the call to any sort of base class constructor. And remember, it also executes this first before it does the body of this. So for instance, if I was to set, let's just say I have a status called stat equal to s, then the order of execution, if I was to create a new undergrad object, is it will go and it will call the student constructor up here with the name given, whatever n was, and use that as the name, run all of this code, and then it will jump back down here and finish the constructor for the derived class. This undergrad code always gets executed second, and this is the only possible way to use constructor code from a base class on the same class that you are doing. Remember that you can't do this. You can't just say student. S is probably a bad thing here, but you know, like, oh, we can't do that because this is a function itself. So when you create a new object like that, you are creating a local variable. You are not calling the constructor for a base class. And then it especially becomes apparent because of the fact that because it is a function body, I can use it like a function body and declare as many variables as I want and write any kind of code that I want here. So I can declare 3 student variables, and then at that point, if you were trying to think of this like, well, that's going to call the student constructor, well, which one of these 3 is going to call the student constructor? O, F, or G? And, well, none of them should because it's kind of ambiguous at that point. So just be careful. The only way to ever call a base class constructor is with this syntax with a colon. We can also use it to initialize variables. I don't think I went over that, and it won't be on the test, but just a offhand mention. You can use it as well if you wanted to have it initialize this, for instance, the status, then you usually have the ability to just call it with whatever the type name is and then put the thing in, and it will call constructors for other classes that aren't a base class of this. I don't recommend this. I think there is some sort of optimization with this in C++ if you call it this way, but I don't really cover it in depth because I don't particularly like that syntax. I think it makes more sense to just call it on things that this should have access to rather than just random classes. But you can put commons and put as many constructors as you want as long as it has access to call those constructors. Then it will do that and use it to construct whatever member you're setting. So there it would have set my stat object, or sorry, stat member. You have to give it explicitly the same name as the member variable. Again, that won't be on the test, just something to mention offhand if you ever see it. Right, so those were our constructors. We use them to initialize, and we can reuse constructors, like we can reuse any functions when we're doing virtual functions if we just call it explicitly using colon or whatever scope resolution is, depending on the scenario. And then the other thing that was mentioned in the chat that we have was deconstructors. So whereas a constructor is called when you create an object, a destructor is called when you delete an object. So if we were to kind of imagine the life cycle of an object, then when it's created, the constructor gets called. Then you just do stuff with it. And whenever it is done being used, either when you delete it using the delete keyword explicitly, or when you let it go out of scope, then that calls the destructor. And again, these are only ever called once. They have no return value, so they are special functions, but they have no return value. They just create an object or destroy an object and do what's necessary to destroy an object, but they don't have any implicit return value. They can't return anything. And one other thing to remember is while we can do a bunch of different constructors, we can define different ways in which you can create an object. Like for instance, maybe you only want this to initialize the name. Maybe if they didn't give the name at all, you wanted to initialize the name to an empty string. There are different scenarios where you might want to initialize or create something. When you delete something, because there are no parameters to that, then you can only have one destructor and it always takes no arguments. So if we ever wanted to write a destructor, it always has to have exactly no arguments. It's like a constructor, not value returning, and the way you specify it, if you remember, is just a tilde and then the class name similar to a constructor. And then recall that a destructor, like a default constructor, is going to be implemented for you by the compiler if you don't write one. And it's totally fine not to write one most of the time because you don't generally need it. But there was one scenario in which we said that it was necessary to write a destructor, otherwise you're going to have an issue. And that was explicitly when you have a pointer pointing to some object that nothing else is pointing to, or whenever you're done with that object that has a pointer to it. So let's say I have an integer pointer here called r, and then let's say in my constructor, we'll throw a size here too. In my constructor, let's say I have it take int s, and it takes that parameter, it takes this s parameter and it sets it equal to the size, and then it allocates that array dynamically, which we'll talk more about in a little bit here. I think we'll probably just segue into it. So if this allocated a one-dimensional array of size, and then kept a pointer to it because that's what the new keyword always returns, then consider that this is a scenario where we actually definitely need a destructor. And the reason we need that is because of the way that pointers work. Pointers are, well, a pointer, they refer to a memory address, but not the actual physical object itself. So they're kind of indirectly pointing to a location rather than representing the location itself. So if I had an EX object, let's just say E, and it had a size, we'll just say is arbitrarily 4, then consider that when you have things that aren't pointers, they're stored directly inside of the class because we can just put that data right in there. But a pointer is something that refers to a location. And so when you have a pointer like this, then assuming that the constructor got called and it allocated this size 4 array, then this points to where this array is in memory. And whenever you do a implicit destructor, one that's written by the compiler that you didn't write yourself, what it does is it just clears out all of this stuff. So it will clear out this 4, and then it will clear out whatever is stored here, which is not the array itself, but a pointer to the array, which, if you remember, is some sort of a number which represents where that thing is in memory. It's its address, right? So maybe this is at location A, let's just say is 1 byte. It's pointing to location A. It deletes not the array itself, but the contents of the pointer, which is just the address. And so whenever you delete something and don't explicitly delete things that are being pointed to, then they're going to be left over and will not have any sort of way to get back to them. So consider if we're doing something normal like this, where the only thing that knows about the allocation of this array was the object that did the allocation and probably needed the array, which is kind of realistic, right? You might expect one object to need an array, but not everybody needs it. Then once you lose this last pointer being the only pointer to this array, nobody knows where it is. It's totally lost because this was the only thing keeping track of where that memory was allocated. At that point, we have what's called a memory leak, if you remember. And memory leaks are especially bad in C++ because the runtime generally does not check for them. And so if you have one, you're not really going to be able to recover from it. You're going to have some amount of memory that's no longer pointed to. You can't find a pointer to it anymore, and it's just going to be there completely unusable and just sitting there, which means that you're going to lose some resources. You might have to request some more resources into the system, which takes time. The operating system has to go out of its way and allocate more space for you, and just generally you're going to have some performance issues. So these are very bad. One of the huge things to avoid in C++ where you have access to pointers. And so we said the way that we avoid having a memory leak, the way we avoid just leaving this space unallocated, is before we get rid of our pointer is to make sure that we deallocate this space before this happens. So we had a destructor here. I didn't actually write anything, but we have access to the delete keyword, which has 2 different variations. There's the normal delete, which is just for a single object, like a class object or an integer or whatever. And then we have delete with the braces, which deletes an entire array. So this here will delete the entire array and get rid of it. And I should probably do one extra thing on this one, even if it's not that particularly bad, is this is going to deallocate this, and then we're still left with our pointer, but it's going to get destroyed once the object gets destroyed. Remember that there was another type of thing which isn't a big deal if you're doing just the destructor, but if you have some sort of object or array and then you do a delete on it and you deallocate it, but this pointer stays around for whatever reason, you still have the pointer variable around, like maybe it's not in the destructor that you're doing deallocation, but just like halfway through the code for whatever reason, and then remember that this was also kind of something that we want to avoid, because this, again, points to some address. Let's just say this time it's A to B. And when you get rid of that stuff, you no longer have access to it. So I might still have some sort of pointer to it, let's just say called P. And if I try to use P, then that's going to be an issue. It's going to cause my program to crash because I'm trying to access memory that I no longer have access to. I've told the system that it's allowed to use it again, so I better not touch it. There might be new variables there, or another program might be loaded there, so that's generally not a good idea to access this in your code. So if I tried to access some member of whatever P is, which I guess we would do this way, then that's bad. That will crash the program. But it was also bad because then you're leaving a pointer to memory that is no longer allocated, and so it gives you some security issues because if somebody got hold of your pointer, they could find out some extra area or a memory that's not allocated and that the operating system might use later. And so, well, that's not going to be on the test, just something to consider is that you don't want to leave any pointers pointing to area that's deallocated already, because you might crash your program, you might make a mistake where it crashes the program, or just have code that relies on the fact that it needs to be there in some way. And then there's security vulnerabilities, and this was called a dangling pointer, if you remember. It's just a pointer to stuff that's not there anymore. And the way that we fixed this was after doing whatever deallocation we have to do, we take our variable and we set it equal to null pointer or null. That way it's no longer pointing to this address and is just pointing to nothing. So it points to actual nothing, which is what null represents, rather than something that used to be there that actually represents a memory address. So if you try to access either of these, you're going to get an error, remember. One is a null reference exception if we try to use a null pointer, and the other one is just a bad memory read because the stuff isn't there. But this one is generally better because you're not leaving access to something that shouldn't be there anymore, if that makes sense. Right, so that's generally when we would use a destructor, is to deallocate this stuff. And if you do deallocate something, then its destructor is called. So if this was not an array of integers but an array of class objects, that would in turn then call the destructor of that class object, whatever it is, and do the code for that. And it just happens whenever you delete something. So I think that about covers constructors and destructors and a bit of the pointers and memory allocation stuff. Let's talk a little bit about inheritance, and then we'll talk about more pointer stuff. Right, so inheritance we did a little bit earlier, but that just is when you want to copy over objects from a class into a new kind of class and be able to reuse things. For the sake of this exam, you just need to know the basics of inheritance. You don't have to know all the virtual stuff we did. That got cut from the first exam. So just know that it borrows things, I suppose. We might have something like this, where we have a class animal. And then it may have a string for the species. In age, maybe just an ID. And if I wanted to make more specific types of animals, then I can do that, and it would be kind of annoying to have a cat class and a dog class and a bird class where I rewrite this every single time, and I do string, species, int age, int ID. If I want them all to be consistent, then remember the way we do that is with inheritance. And the way you do inheritance in C++, so let's just say we have a cat class here, is you give the name of the class as if you were creating it normally, and then you do a colon, and then whatever type of inheritance you want from the parent. And so what this does is it allows us to copy over any sort of members that existed in the animal class and copy them over to the cat class. It also allows us to borrow functions and be able to call those. And even if we don't have direct access to these members, like these ones are private in this example, then we might still have functions that are able to access them, and we'll be able to do stuff based off the base class. And then we can expand upon it too, so maybe a cat has an integer for whiskers that's just only part of a cat, so it makes it unique, and it might have its own actions like void, meow. And we're able to build upon everything that the animal has and add more to it by doing a derived class. Remember, there were these class hierarchy diagrams that we've been drawing just to kind of represent this. So we have this animal class, and then we have maybe some other classes that inherit from it. So we've done a cat, we could also do something like a dog or a bird, and they inherit. And whenever you have inheritance, there's that terminology of it's an is a relationship. So a cat is an animal, and a dog is an animal. So an is a relationship is when something, well, is that thing. And that means that it's guaranteed to have all the members that that object has, or that that class defines. So both a cat and a dog are animals, and in that regard, they're guaranteed to have species, age, and ID, even if the cat class and the dog class have their own functions and members that make them stand out. Then we can at least be guaranteed that they have everything that makes them an animal. They're guaranteed to have it. And then there was some notion of having a has a relationship, which doesn't have to do with this class hierarchy, but is just the idea that they can have their own attributes. So the cat has whiskers. It has a relationship with an integer. It has a specific whiskers object being just an integer that it contains. So that was the general idea of inheritance, and it has applications in that we can do something like this, where I could have an animal array, probably of pointers, because C++ usually makes you do that. We'll just call this a array. We'll just allocate it to be 4. And we have the ability to store multiple things of different types, but of the same parent inside of one single type. So for instance, I could have a cat here, and then put a dog at position 2. And this ends up being totally fine because a dog and a cat are animals, so it's okay for me to store them in an animal array or vector, whatever you prefer using. And then I can put things that are similar in some way, that have some sort of parent in this class hierarchy, into the same data structure. And it becomes really nice, if you remember from the game object example we did, where we can have a player and an enemy and items and all that kind of stuff that all inherit from a single game object class, store them in one thing, and then give them common traits that we're guaranteed they have. So for instance, I can print out the species of any given item, assuming it's allocated, in this array, because we can be guaranteed that they're all animals. So if the dog set its string species to dog, and the cat set its string species to cat, then they'll print different things, even though they're stored in a variable that is just the same data type, all being an animal. So it allows us some code reuse, which is kind of the purpose of really almost all programming structures, is to be able to reuse code and make life easier. And being able to do this with parent classes is pretty useful. I guess on that note, last thing about inheritance, remember that we're allowed to do something like that. Where we set something equal to its base. So a dog is an animal, therefore I can store a dog in an animal variable because we can be guaranteed that anything a dog has, even if it has some extra things, it still has to have all the things that an animal has. So this is an okay thing to do. That's all right. But this here is not okay to do. Because if I had, for instance, a dog has, I don't know, a function called bark or something, oops, then by doing this, we're not guaranteed that the animal has all of the members and the functions that a dog has. So for instance, if I need a dog to bark and I try to do that on the next line here, then this is not going to work because of the fact that an animal can't just bark because only dogs can bark. So we can't be guaranteed if you go from top down on this class hierarchy that it's going to work. In other words, if you violate the is a condition, then it's not guaranteed to work. And something like this, the compiler is going to not let you do, but you do have the ability to do this in certain scenarios if you cast it. I'll just put it as a note over here, but if I did this, where I casted the animal to a dog on this line, then that would be okay. It would allow you to do that because it assumes that you know what you're doing if you do that. Maybe there is still some reason that you want to do this, but the compiler is not going to explicitly let you do that. Or sorry, is not going to let you implicitly do that. And on top of that, if you do it, it's going to potentially have some errors if you try to do something like this that's invalid at runtime. And it can only ever check it at runtime. The compiler can't take your word on it, or the compiler does take your word on it, but it's not going to be able to verify it ahead of time that you're actually correct in what you're doing. And in fact, you might not even necessarily be able to know ahead of time depending on your program as well. So just be careful if you're doing it backwards, but remember that we can set things based off that is a relationship. It's totally fine. And a question in chat would be, would that be considered upcasting? Yes. Yeah, so this should be upcasting, I believe, because it would go up the hierarchy, so we're casting a dog to an animal. I think I just deleted. This would be upcasting here. That's totally fine to do, because a dog we can cast to an animal. That's totally fine. And even though I'm not explicitly casting it, it is changing the type of the variable. So that would be upcasting. The other one would be downcasting because it's going down the class hierarchy. So upcasting, good. You want to do that a ton. Very helpful. Downcasting, be careful with. It can give you runtime errors, and you can do it, but it's not recommended. Most of the time. There are definitely scenarios where you can use it, but generally try to avoid it. Cool. So I think that's everything on inheritance. Next part I think was pointers and dynamic memory allocation. Yeah, okay. So we can do that really quick. We talked a little bit about the dynamic memory allocation earlier. But let's just talk a little bit about pointers again first. We remember that there's memory, which is just usually your RAM, and it represents a space where you store data, instructions like add, subtract, that kind of stuff. But it's just like some place where binary goes. And when we do any sort of variable, let's just say I do int x here, then what happens is this goes somewhere into memory and it allocates that space and says, okay, this is where the integer x goes, and this is now where x belongs. If you do anything to x, it's going to belong in this space. And then we said that there were addresses for these, so this might be 0, 1, 2, 3, 4, 5, 6, 7, and 8. And so the address of 8 here is always denoted by wherever the top of the object is. In this case, it's hex 3. So that's the location of X. Whenever we do a pointer type, we'll just do that yellow here. So let's say I have an int pointer called P. And remember, the way you get the address of something is with the ampersand. So if we do ampersand X, it will return the address of X, which is the top of X, which is this 3 here, and it will store it in the variable P. So P is going to point right here. P gets its own memory allocation and has its own pointer to itself, but it's just generally a address. So this will be storing the number 3 here. It's this hex string, and it represents where something is in memory. So by doing this, we're getting the address of X, which is 3, and then storing it in something that represents addresses, which is what a pointer is. And we have the ability to do multiple types of pointers. There's no difference in the way that they do addresses. Really, they just all point to a location. It's only when you go to use them that there's some sort of difference. So I'm going to go ahead and just do a void pointer called v, and also set it to the address of X. And if I do that, then I'm going to have a pointer called v that points here as well. And so if I was to go and write some code here that does, let's just say cout p with the star, so the dereference, if you remember, the star gets the value of something located at that pointer, then this is going to return whatever X is equal to. So let's go up here and actually set X equals like 7, we'll say. Then doing this will print the number 7, which is stored at the location of X. But if I went and did something like this, where I try to dereference v, well, this is going to be a compiler error because it's a void pointer, but it doesn't figure out what to do until it actually goes to the location and knows what type it is. So we'll say, I don't know, we'll turn this into a character pointer instead. Then instead of printing the number 7 here, then, oh, I need to actually put the letter C, then this will print something, probably the null character, if anything. And that's because it's pointing to a location where an integer is located, but it's trying to treat it as a character. So remember that a pointer, there's no difference in the way the pointers are stored. They're all just addresses. They're all the same size. There's no difference between them. You can use them pretty much interchangeably, aside from the fact that you may have to cast them. In fact, I probably need to do that here. Cast this to a character pointer. But their usage is determined by when you actually go to access that data, which is done with the star generally. Then there's a difference there because the type of pointer that you're using dictates how the binary at that specific location is going to be interpreted. So whereas an integer we've said is like 4 bytes, it's going to represent this and be in some sort of 2's complement representation. A character is just 1 byte, so it's only like one of these blocks on this thing. So if I try to go here and treat X as a character, it's not going to just be the character 7, it's going to be probably just some random garbage. If anything, it'll probably be like 128 if I had to guess. No, I guess it starts with a 0. It's probably no, like I said earlier. So just be careful with that. Generally, you're probably not going to want to do this anyways, but if you do, just make sure that you're using the right type. And we were using a void pointer earlier. Remember that a void pointer is just a pointer that has no specific type, and because of that, you can't do things like print it immediately because it has no type. It doesn't represent anything. It just is the address to that location. And the reason we use void pointers is if you want to change what that thing is later, or the way that it's interpreted, then you can always cast whatever the void pointer is to whatever it is you want to interpret it. So for instance, if I did want to interpret this as a character pointer, I could cast v to a character pointer and try to read X as a character. But generally, you don't want to do that too much. The void pointer maybe a little bit, but definitely not this. The last thing with regards to pointers is, remember, we have the ability to do arithmetic with them. So you can do plus, minus, plus, plus, and minus, minus, but not weird operations like multiplication. Yeah, I was gonna say this is good. You do these ones. You can't do stuff like multiplication. You can't do division. You can't add a pointer to a pointer. So while you do have addition and subtraction, you always have to be adding and subtracting by integers. Only integers, not pointer to pointer. That's not allowed. And no modulo. Pretty much everything else, they're not allowed on pointers. You can't do that. And remember that what this does is it just moves that thing in memory. So for instance, if I tried to do the location x plus 1, then that is right there. And if I tried to do x minus 1, then that's somewhere up here, a little bit off our memory. That's where this is, and that's where that is. And the thing to remember about this is when you do addition or subtraction with pointers is that it doesn't go on a byte basis, it goes based off of the size of the variable. In fact, I shouldn't be using x, I should be using p as the pointer, right? Then this is going to jump over the integer. So if p is pointing right here and I do p plus 1, it's going to go to the next block where an integer would be in memory rather than just jump like one at a time in the memory space. So this jumps 1 up, and then if I did p minus 1, it would jump 1 integer backwards. So assuming there's some integer located here, it'll jump 1 backwards. And generally, you don't have to remember that difference when you're programming, because the common application of this, if you remember, was just arrays. So I could allocate an entire array of things in memory. And then let's say there's 8 things here, I think. Then if I have some sort of pointer here to an array, remember this is array 0, this is the 0th item in the array, and this is the first item in the array. They just kind of get allocated all right next to each other, and we can use this to access them. So another way to access this block right here would be to do it as just R. You can dereference it directly. That's R. Or you could say R plus 0. Although that's not really going to do anything, right? And this one would be at R plus 1. So we can use these to traverse an array. I don't recommend ever using this syntax. There's almost never a reason to do this, but it is totally an option to do. And if I wanted to access the second element, it would be at R plus 2, and the third element would be at R plus 3, etc. So question, is this for an array of ints or any type? So for any type, it will work. It knows how big any given type is. So while I'm doing integers, and those are specifically 4 bytes in memory, if you do a character, it will know that that's 1 byte, so it'll skip 1 byte at a time. Whenever you do plus 1 or plus whatever number, it'll skip 1 byte for how many ever numbers that is. If you do a class type, it will skip by how many ever bytes that class is. So, you know, if a class had 2 integers in it, then that class is going to take up 8 bytes of space because it contains 2 integers. And so whenever you do a plus 1 with a class pointer, it will go by exactly that much. So it bases it off the type rather than off the byte addressable stuff, which is how memory actually is, right? It's just a bunch of cells of bytes. It's based off the blocks of whatever that data type is. And so because of that, that's why I definitely recommend never doing this stuff where you use different data types, because an integer and a pointer, for example, one is 4 bytes and one is 1 byte. So if you start doing addition with these, you might get a little confused and have bugs, and it's really easy to make mistakes. So yeah, just consider it's based off the block size. I feel like there's something else I want to mention. Oh, right. Remember that you have the ability to access it like a normal array if you ever have a pointer to things that are contiguous in memory, and you should definitely try to use them like an array. It's way easier to read in my opinion. But if you ever try to dereference an array pointer, it's always pointing to the top. So you'll always get the first item because the first item is always at the top. So try not to dereference an array, I guess, because you might get unintended behavior. Right, I think that's about everything on pointers. We should probably just end things off with the dynamic allocation. So dynamic allocation is just when we use the new keyword, and it's especially useful when we're doing arrays, because unlike in 135 where you were married to a specific size for the array, you couldn't change it once it happened, like this. If I did R4, then this array is always going to be 4. I have no way to change it, and that's not that good because of the fact that if we have more than 4 things that we need to put in this array, then we're out of space to put it into, so we're kind of just going to have to throw stuff out. And if we only have 1 thing that we need to put into the array, then that's 3 spaces wasted, and so there's memory that goes unused. And so static arrays generally, unless you know ahead of time exactly how many things you need to put into an array, are not too useful, but we can decide how much things we want in an array if we do dynamic allocation. So for instance, if I had a file where I read the size, let's just say, of how many things I can expect to put into the array, I can then dynamically allocate it instead of make something and then kind of fill just how much ever needs to go into it. So we can do something like this. Remember, it always has to be a pointer when you're doing arrays like this. We'll just call this R2, and the way you do the allocation, like we've been doing earlier, is just with a new keyword, and then you give the square braces followed by how many ever things you want to allocate. So let's just say we read the number 10 here, then we can allocate 10 things. And this is great because if we ever, during the course of our program, need to get a different size array, we totally have the ability to do this. So if I figured out that this is 10, but then I need to read more of whatever this integer is to the array from the user or something like that, then we could go and resize this array and basically make more space. So for instance, if I knew afterwards that I needed to allocate it to be 15, then we could allocate a new array that's of size 15. And obviously you wouldn't want to do magic numbers, you would probably have a variable, but for the sake of our example, you would allocate more space. You could then copy over all of the elements. So we could go for int I equals 0, I less than size, I plus plus. We don't even need that. And just move everything over from R sub 3 into, R3 sub I from the second array. And then deallocate the old one so that we don't waste space. And this allows us to create more space for ourselves in an array while keeping all the contents of the old one. At the cost of performance, because we do have to do some copying over here rather than just having all that extra space wasted. So this potentially is faster if you end up wasting space, but it's just not generally good. And just remember, for the sake of our thing here, that when you do this, let's just say I have R2 here. And I go and make the variable called R3. What we don't want to do is just do the line of code R3 equals R2, because these are pointers, remember, so all that says is point this here, and that doesn't solve our problem. All that does is it just overwrites our thing. And if you did this after the allocation of R3, like for instance here, you allocated R3 to be 15 integers, and then you just, instead of copying them all over one by one like I did here, you just set the pointers to each other, then this would do an allocation, right, of a bigger array, and then it would just go here and point here, and then now we have a memory leak. So just consider we always need to copy element by element. We can't do like just direct pointer stuff. So if you ever want to copy an array, you need to copy each and every one of these elements into the new thing. Right, so that's our dynamic allocation, and then you always want to deallocate any space you're done using, so we could delete that there. And then one last note about this, and just pointers in general, so let's just make a note here, is consider if I had an int pointer called x and y, and I dereferenced x and stored the number 3 in it, and dereferenced the number y and stored a 3 in it. And remember that when we do pointers, does anybody remember if this was true or false? Oh, you're right. Y is not a pointer. Thank you. Good catch. Alright, I can just do it faster, right? Just put a star there. Yeah, so is this true or false? If I have two pointers, x and y, I have them both be 3, and then I compare them, and yeah, I see the right answer in the chat. So this is false, because even though this is 3 and this is 3 in terms of their contents, these are pointers, so this is comparing their memory addresses, whatever those may be. We'll just say, are these random numbers? Something like that. So be careful when you're doing pointers. You can't just set them directly equal with them either, because they point to a location and you can't get their things, so you need to dereference it instead. And same thing especially goes for class pointers as we get into the operator overloading assignment. Make sure that if you compare two objects that have pointers to them, that you have some sort of equal overload for that, and that you're not just comparing them directly, because it is going to compare the pointers instead. And then, sorry, one other thing, just want to come back up to this again. This was the notion of a deep copy. I just wanted to remind everybody that that's the word we use. So if we copy everything over one by one and make separate copies of it, and that's a deep copy, whereas the version I did earlier, that was a no-go, was called a shallow copy. Which just means the pointers point to the same location. You don't actually make like a real copy, it's just they point to the same thing. Okay, I think that was everything I wanted to go over. Just kind of a quick recap. I guess on that note, did anybody have any questions that they had, or any topics that they still wanted more on? We could definitely work through examples as well, if you would like to. I guess on that note, while we have extra time, does anybody have any questions on assignment 4, since that's due tomorrow night, I think? Singly even? Okay, fair enough. Yeah, let's talk about that. So let's talk about the singly even from the assignment 4. So if I remember right, the way singly even works, well, we kind of have to know about the odd order first. So let's talk about the odd order. there were three cases when you're doing assignment 4. One was singly even, one was doubly even, one was odd order. So odd is if the size of the square was odd numbers, singly even is if it was a even number not divisible by 4, and doubly even was if it was divisible by 4. So an odd order, let's just say, is something like 3 by 3. Draw a straight line. And the way it worked is you always start at the top number here in the middle of the first row, and you place your first number. So just as a reminder, we're trying to generate a magic square, something that where all the rows and the columns and the diagonals equal the same number. We want to start here, and then basically what we do in the odd order is we always just go top right, and then we wrap around if necessary. So let's just keep track of these indices really quick. This is at 0, 1, and 2, and this is at 0, 1, and 2. And so if I try to move upright from this 1 position, it would go to the position -1 for the row and then 2 for the column. If you ever encounter that scenario where it goes out of bounds, less than 0, then you want to wrap it around back to the bottom. So this arrow instead is going to, instead of going to this space up here, which doesn't exist, it's just going to drop down to the bottom. It's just going to wrap around. And then what you do for this algorithm is you essentially just keep going. So if I go up right here, it's going to wrap around to this one. And if the next space that you're going to hit is already filled with a number, what you do instead of go to that position is go to the one below it. So we would go here to 4, and then we would keep going up right, 5 and 6. And technically, if you're in the top right, you are going to hit this location. So if you're in the top right, you want a separate check, because this would make us want to go down. So we would go down here, because the next place we would go if we wrapped around would be 4. And then we would keep going with this thing. So we wrap around up to there, and then wrap around to there. And then if we were to add up all of these rows and all these columns and all of these diagonals, then they should add up to 15. So the general strategy for this is you try to go upright. If the space is occupied, you go down instead of upright. And if you were to go out of bound, you can wrap around using something like modulo, or just check if it's greater than the size, then move back to 0. And so when we do the singly even order, then it's going to use the odd order on the board, but essentially just split it up into 4 parts. So for instance, if I had a board like this, let's just say it was 6 by 6, then what it'll do is it will split it into 4 subboards, each 3 by 3. And then we would solve that odd problem in each of these 4 quadrants, basically. So I think, and somebody can correct me if I'm wrong, but I think it was something like this, where this was A, B, C, and D, where you go in this specific order, you do the A1 first, the B1 second, the C1, and then the D1. And the general idea is that they're basically all the same thing, but the numbers are slightly different. So I think it'd be easier, rather than me write it out, if I just pull it open the assignment. Okay, so we have the assignment 4 thing somewhere in here. Yeah, oh, there it was. So we have like this ABCD thing, and what we do is essentially in each of these boards we're going to solve the odd order problem and then kind of keep the numbers. So on this one, you can see here, this is like the A subboard is these numbers, and because this one is 10 by 10, then each of these subgrids are 5 by 5. So you can see this one goes from the number 1 up to the number 24. And then we have this next one, oh sorry, I guess 25, there must be a 25 somewhere. It should be right here, am I right? Oh, or is this one that's filled out and it's gonna be like somewhere else? Let's see the number 25. I might just be blind. That should be 26 though, but there should be 25 somewhere in this, and I think I'm just... not seeing things correctly. But anyways, like this would contain all the numbers 1 through 25, and the top left one, this A here. And then this B is going to contain the numbers 26 to 50. And then this one's going to contain 51 to 75. And then this one is going to contain the numbers 76 to 100. So if this is a 10 by 10 subgrid, we expect all numbers 1 to 100 to be in here, and then each of these like 4 subgrids are going to contain the 4 like blocks that lead up to 100 in groups of 25. And so in each of these subgrids, what we want to do is we want to do the odd order algorithm, but just over that subgrid. So for example, here if I did A, we would essentially fill it in the same way we did this one, and when it goes out of bounds, it instead wraps over to here rather than pouring over into another subboard. Right? So our challenge on this one, at least the approach that I suggest doing on this, is how do we break this up in such a way that we can do the odd order, reuse our code, and have it just work on these 4 subboards. So you can make 4 calls to the odd order function and just have it work that way. So what I want to talk about a little bit, without giving you the code directly, is how we can do that. So let's say we take any of these subboards arbitrarily and draw them over here. And what we're going to need for this is we're going to need a little bit of information to be able to handle going through this subboard specifically. So we want our indices of the subboard rather than indices of the full board. So when you're solving problems, generally when you're doing computer science problems like this, I think it helps to create new variables that represent values specific to whatever problem it is you're solving as like the broken up problem and not relative to your big problem. And so we'll come back to the big problem of the big board later, but let's just say that this here we have X is the one in red, and or no, I guess that would be the other way around. X is the one that's going to be in blue, and Y is going to be the one that's in red. And the way we can tell these is they just all start counting from 0 to the size. So they go from 0 to whatever the size is. And so if we keep track of whatever the size is in this subboard in the context of a problem, then solving it should be totally fine. It's the job of whoever is calling this now to give it the correct size for this like sub problem to work. So if they give us the size, then hopefully our problem should work. But we know that this goes from 0 to, I guess, size minus 1, really. And it's going to count over all those numbers. And so assuming your algorithm works, you know how to do this, where you go 1, and then you put the 2 here, and then the 3, 4, 5, 6, 7, 8, and 9, and you know how to do that, where you move it upright every time unless there's a collision, and you move it down, then that's great. We can do that relative to the X and the Y and kind of solve our problem. Now, the issue for that comes from 2 things when we try to apply this to the big board. So this is great. This solves our problem for whatever subboard, and it will put the numbers in the order. But if I was to go and try to call this with just the information about the size and to try to call it on all the subboards, then it's just going to generate this like 1, 2, 3, 4, 5, 6, 7, 8, 9 in each of these 4 quadrants. And that's not what the actual answer is, right? Because it's like all these ones start counting at, I guess this one starts counting at like 10 in our example, right? And then this one starts counting at 19 and 28. So all of these numbers would be generated in the correct order, but not the right numbers. Plus, on top of that, if we just use these X and the Y, then they're only really in this subboard. So if I try to access the elements like 0, 0, and 0, 1, and 0, 2 in this big board, then that's only the ones that are in A. It never applies to the B, C, and D. So we need to solve those 2 issues, putting it into the correct position, and then also whatever the other thing I said was, which I'm now forgetting. Oh, the counter, right? So I think the counter is pretty trivial. What we do is we just pass this a counter, being whatever number we want to start counting at, And you can share that across all functions. So we could make this a pass by reference if you were to make this a separate function and just have it count up. And that solves that problem relatively easily. So for instance, if this was to start at the number 10 and do the next one, then it will go like 10, 11 down here, 12, 13, 14, 15, 16, 17, and 18. It would generate all those numbers and it would start counting at 10. But it would still follow the same path, right? The point is that our algorithm does the same thing every time. We just need to give it a different starting point. So I think one thing that would help if you decide to write this as a function is if you give it the counter being the starting number to count at. And then the other thing we need to consider is how do we put these in the big board? Because if we just use these x and y values, then they're always relative to the top left part of the board because, well, that's where 0, 1, and 2 are, right? You always start counting at the top left. And so the way to solve that is we just do things using the top left of the board and we kind of just add things to it. So consider here, let's just say I have C. The top left of C is at the position 0, row 0, column 3, right? Is where this top left is. And if I look at all of the positions here, so let me redraw this a little bit. So let me say I redraw that subboard. This is just C. This is the C subboard. Then if I do those relative positions that were like the x and the y that we had earlier, then it would look the same as any other subboard, 0, 1, and 2. So when you do your function, you can use those consistently, always just have them be from the 0 to the size -1. And we know the top left. So the extra context we need now is the top left coordinate, which is, for this problem, 0, 3. Right? This is at position 0, 3. And then what I'm going to do here is I'm just going to write out the absolute numbers. So if we were to look at this big one, this is column 3, column 4, and column 5. Right? If we count from here, 0, 1, 2, 3, 4, 5. So this would be 3, 4, and 5. And then as far as this column goes, these are just 0, 1, and 2, right, relative to the big array. So this is 0, 1, and 2. Now, something nice to consider is that if I was to access, let's just say, this one here, then this is at position 0, 4. The way that you can calculate this at any given time is just to simply take the top part of the board and just add wherever it is that you are in the relative board. So with those x and y that we're keeping track of, then this is at position 0, 1, right? I guess that should be in blue. So if we take the top left that we keep track of, and if you pass that to the function, you can always know where you are in the whole like absolute board, the big one, by simply just adding the two numbers together. You can take whatever that top left is and then add your x and your y that you just keep to look through the array and add it to it, and it will always give you whatever the global thing is. So here are 0, 3. If we add the x and the y just element-wise, then we get 0, 4, which is where we want to be in the absolute board. And this only really comes in when you're solving your problem for setting numbers, consider. As far as solving the problem itself, consider that we were able to solve this problem and like go through and go in the correct order without having to know anything about the global board. We can just use our x and our y in the context of our problem and just loop all the way around and generate these numbers. It only ends up mattering when you actually go to set the number itself. So you only need to do this calculation where you add the x and the y values when you go and actually set the counter equal to some value in the global array. So that's just an approach I would suggest for this one. It's how you would do this with a function approach, which I think, in my opinion, is easier. Like sometimes harder to just wrap your head around the problem solving at first, but you know, if you have a function that can generate this over any subboard, then your singly even part of your program is going to be super easy because you just do 4 function calls. And it's just like, you know, whatever number, the top left of this, so you give it the top left of that, top left of that, top left of that, or top left of this one first, and then top left of that one. and just add the numbers in the function. So that's the way I would recommend doing assignment 4. It's the way I put in the images if you've seen them on Discord or Canvas. And I would definitely recommend doing it that way, but if you're super stuck, you can kind of think them through one at a time and use whatever the numbers are, like dividing by 2 and finding where the positions are, but I think you still need that line of thinking in order to do it correctly, if that makes sense. And I think we're out of time. So hopefully that helped for anybody who's still stuck on assignment 4. That it can be hard to wrap your head around the problem solving at first, but try to break it up into sub problems and then apply those later. Cool. So I'll stick around if anybody has any more questions on the assignment or any more review questions. We don't have to meet on WebEx on Thursday. You can just go straight to the exam. Again, it'll be at 5:15. It's on Canvas. So best of luck on the exam, and I will stick around if you have questions.